Hello everybody, my name is James, and today I'm going to be talking about how to convert MIPS instructions into machine code, and vice versa. This video assumes that you know how to work with both hexadecimal and binary numbers. First, we're going to convert the following MIPS instruction to machine code. Sub T0 S4 S5. Okay, here we have the R-type instruction format, and as you can see, the first 6 bits are the opcode. This section determines what type of instruction you are actually using. The next fields are the RS, RT, and RD fields. These correspond to your argument and destination registers that you're using, and as you can see, they are each 5 bits wide. The next register is the shift amount. This is only used for shift instructions, so thus it will not be used here. And last we have the function field, which is also 6 bits wide, and this is used to determine what type of R-type instruction is actually being implemented. Okay, first off, we go to our MIPS reference sheet and look up the subtract instruction, and as you can see here, the opcode is 0 hex, which corresponds to 000000 in binary. As you can see, we had to convert that into 6-bit binary number due to the fact that the opcode is a 6-bit field. Similarly, the function field is 22 hex, which corresponds to this 6-bit binary number. And again, this had to be 6 bits wide because the function field requires 6 bits. And a side note, all R-type instructions have an opcode of 0. Thus, whether you're working with subtract, add, etc., any R-type instruction, you know just off the top of your head that the opcode will be 6 zeros. Next, we need to determine the register numbers. So as you can see here, T0 corresponds to register 8 in MIPS, which corresponds to this 5-bit binary value. And as you can see here, this has to be 5 bits wide due to the fact that the RS, RT, and RD fields are all 5 bits wide. And similarly for S4 and S5, we found their decimal equivalents to be 20 and 21, and here are the resulting 5-bit binary equivalents for those two registers. Now that we have all of our information, we can now insert it into the R-type instruction format. As you can see here, the order of the registers in the instruction does not match up with the order of the instructions in the format. As you can see, the arguments S4 and S5 come first down here, but in the instruction itself, they come after the destination register, which is RD. So, as a quick recap of all of the info we've previously discovered, we can now insert them into the instruction fields to obtain the following machine code version of sub T0 S4 S5. Next, we're going to convert a branch instruction into machine code. Here's the typical I-type instruction format. As you can see, it has a 6-bit opcode field. It has an RS and an RT field. However, in contrast to the R-type instruction, which had an RD field, a shift amount field, and a function field, the I-type instruction has a 16-bit immediate field, as seen here. First, we're going to start off like we did with the R-type instruction and find the opcode for the branch unequal instruction. As you can see here, the opcode is 4 hex, which once again corresponding to its 6-bit binary equivalent of 000100. Next, we're going to determine the register numbers. As we can see, T5 corresponds to 13 decimal, and S0 corresponds to 16 decimal. Now we must compute the branch target address. This is computed by adding PC plus 4 to the 16-bit immediate field. Now, we must determine the 16-bit immediate field, also known as our branch offset. This is done by first computing our current PC plus 4 due to the fact that the MIPS machine has already incremented our PC at this point in time, and subtracting the branch destination address. This will result in the absolute value of the distance that we must branch to. However, this distance is written in bytes at this point, so in order to get it into a word address, we must divide the result by 4. Next, we must extend our result to 16 bits if it's not already 16 bits, so that it fits into the 16-bit immediate field. And finally, if our branch offset happens to be negative, we must form the 2's complement of that negative number. So, first off, we compute our byte offset, which is computed by taking our current PC, adding 4, since this has already been done for us by the MIPS machine, and subtracting where we want to branch to. And this results in this byte offset right here. Now, as mentioned previously, we must compute the word offset by simply dividing our previous value by 4 to obtain this value right here. Transformed into binary, we get this value right here. Now, because this value is less than 16 bits, we must extend it to 16 bits by simply adding zeros in front of it, since this is a positive number. Now, as you can see here, our branch offset is actually negative, since we start off at a higher address up here and go to a lower address down here. Thus, we must form the negative number of the absolute value of the offset we've just computed. So, in order to do that, you simply complement all the bits, resulting in this value here, and then add 1 to get our final branch offset value. Now that we have all of our information, once again, we simply insert it into our instruction fields. In contrast to the R-type field, which had the destination register in front followed by the 2 arguments, the branch if equal flows just like it does in its instruction format. RS comes first, followed by RT, and then the 16-bit branch offset goes in this field right here, which helps determine where to branch to for the loop. A quick recap of all of the information we've computed. And lastly, here it is inserted into the I-type instruction format. Now, our last example, we're going to be working backwards. We're going to be given machine code, and we're going to convert it into a MIPS instruction. We first start off by looking at the opcode and seeing what its corresponding instruction is on the MIPS reference sheet. As you can see here, our opcode is 3, which corresponds to the jump and leak instruction. So, at this point, we know that we're working with a jump and leak instruction, and we also know that all jump instructions have this following format right here. So, the last 26 bits of a jump instruction are used in determining the final jump address. And the jump address is computed by the following. First, you concatenate 2 zeros at the end to make it into a word address. Then, you add the 4 uppermost bits of the current PC to the 4 uppermost bits of your final jump address. So, we start off by taking our address field, adding the first 4 bits of our PC, which in this case is 1, which expanded into 4 binary bits is 0001, and lastly we concatenate 2 low order zeros. When you convert this number into hexadecimal, you get the following value. Thus, this machine instruction corresponds to the MIPS instruction jump and link to address 0x1041001C. This concludes my video. I hope you guys enjoyed it.